Alright, hey, my name's Emory, and I'm doing section 4.6, number 21. And the question reads, a boat is being pulled toward a dock by a rope from the bow through a ring on the dock 6 feet above the bow, as shown in the figure. My figure. The rope is hauled in at a rate of 2 feet per second. And part A is asking us, how fast is the boat approaching the dock when 10 feet of rope are out? So, it's a related rate problem, so we have to figure out what we seek and at what time. So, or at when, or when. So we're seeking dx dt because down here I just labeled this x to make it easier, because that's the variable that you're trying to find. And when r, the rope, is 10. So, and let's go to the toolbox. There's not really much that you can put in the toolbox at this point, so what it gives you is the rate at which the rope is being hauled in is at 2 feet per second, so I just threw that in there. Now you have to find an equation. Well, first you have to find what x is. So, to find what x is, you have to use the Pythagorean theorem. And through using that, you find out that x equals 8, even though a perfect right triangle is 6, 8, 10, so you kind of just knew. But now you have to find an equation that relates dx dt, what you're trying to find, with the things that you have, which might be dr dt. So let's just look at the Pythagorean theorem, right? This squared plus this squared equals this squared. So let's go 36 squared plus x squared equals r squared. We're not going to put in 10 yet. Since 36 is a constant, you have to take the derivative of this. Since 36 is a constant, it cancels out. The derivative of x squared is 2x times dx dt. And the derivative of r squared is 2r times dr dt. Now, all you have to do is plug in the variables. X is 8, as you can see from up here. R is 10, as you can see from the problem when r is 10. You don't know dx dt, and you know that dr dt is 2 from the toolbox. So plug all those in, and multiply it out, then divide, and then you get that dx dt equals 5/2 feet per second. So that's the rate at which the boat is approaching the dock. Now, over here, on part B, the question reads, at what rate is angle theta changing at that moment? So basically, you're trying to find d theta, right here, d theta dt when r equals 10, same moment. Basically, you set it up, you can really look at it from any way, but I just decided to take the sine of the angle. So sine of theta equals x over r, right? X over r. Opposite over adjacent, so katoa. So basically to find theta, you have to take the inverse of theta, which gets you x over r. The inverse sine, you have to multiply both, you have to take the inverse sine of both sides, which gets you theta equals the inverse sine of x over r. Now, when you take the derivative, and then you have to take the derivative of both sides. On the left, you get d theta dt. On the right, the derivative of the inverse of inverse sine is 1 over the square root of 1 minus x squared. So I plugged in x, and one thing you have to remember to do is multiply by the chain rule. Now there's a chain rule here, and that's a quotient rule too. So basically you take the quotient rule of this, which you have here, and you do the same thing that you did over there. You plug in everything, you put it into your calculator, and ultimately you get d theta over dt equals -3/20 radians per second.